All right, hello everybody. So this is the review session for EGME 541, Finite Element Methods for Mechanical Engineers for Midterm 2. Okay, so I looked up the poll on Canvas, and it looks like the winner for this round is going to be Isoparametric Elements. So I'm going to spend the majority of this review talking about that, because there's a lot to talk about with regards with that, especially with a lot of the questions I'm getting from the homeworks over the weekend. And then the second place was strong and weak form. So I'm guessing what people want to look at are kind of weak form solutions, just kind of based on questions people asked for that homework. But we'll go over that at the end. But the first thing I want to go over is just isoparametric elements. Okay, so let's go ahead and jump right in. And let's start with isoparametric elements. And so the idea with isoparametric elements is to basically help us perform integrals in 2D. Okay. And in particular, these are integrals over our finite elements. Okay. Because oftentimes, when we're talking about, performing finite element analysis on like an arbitrary 2D mesh, oftentimes we're faced with elements that have kind of a very arbitrary orientation. Okay? So we're going to have something like this, where this is node 1, 2, 3, 4. Okay, right? And then we know from from previous lectures that if we want to perform finite element analysis on this, we have to compute several integrals over this element. Okay. Okay. And these integrals are going to give us things like our element stiffness matrix and our element forcing vector. Okay. And so I think previously what we've done, at least for the four node rectangle, is we've done element stiffness matrices when the rectangle looks nice like this. Okay? When basically the sides are straight and everything looks nice. Okay? And so when the 4-node quadrilateral takes this nice form right here, what we can do is we can easily kind of form our shape functions and shape function derivatives. Okay. Okay. And this is nice because when we can form our shape functions and shape function derivatives, when we compute our element stiffness matrix and element forcing vector, the only thing we have to do is just kind of plug and chug this stuff in. It's a lot of plugging and chugging to do, but it is just plug and chug. Okay? And so, for example, our element stiffness matrix is given by the following. Okay. Right? And so our element stiffness matrix in 2D is given by the double integral of the gradient of W, our weighting function, times K times the gradient of T dA. Okay, and then remember, these gradient functions right here, when we put these in terms of our shape functions, they end up having, our shape function derivatives. So it'd be like dn1 dx, dn2 dx, etc., etc. Okay, and so the same thing is for that. But when our elements have kind of this arbitrary orientation like we have above, this becomes more difficult because it's not so easy to form the element stiffness matrices. Okay, and so the ones basically that we went over, in the previous week on heat conduction, those won't apply here because these sides aren't perfectly, they're not parallel to each other, and the nodes can be kind of any which way. Okay, and so basically, in order to help us perform these integrals, what we're going to do is we're going to take this element here and then map it onto an element that looks much nicer. So we want to map it onto something that looks like this. But if we're going to go through the trouble of mapping, an element, we want to map into something that's standard that we're going to use for absolutely everything. And that standard element is called the isoparametric, element. Okay. And so our isoparametric element is going to look like the one on the bottom left, but we want to make it so that the coordinates of this element are nice. Okay. And so let me draw the isoparametric element for you, and then I'll write out the shape functions. Okay. And so we're still going to have a 4-node quadrilateral, just like we did before, and the nodes are numbered. Take note of the specific node numbering, because that's really important when you're doing these kinds of problems. So node 1 always starts in the bottom left. Then we kind of work our way kind of counterclockwise from there. So node 2 is directly to the right, node 3 is above it, and node 4 is to the left of that. Okay. And the coordinates of this are going to be -1, -1. This is 1, -1, 1, 1, and this is -1, 1. Okay. Let me adjust a different color. And so since we've mapped it onto a different, system here, our coordinates are just to kind of denote, or just to kind of stay organized and to note that we've moved into a different kind of frame of reference, we call these variables something else. We don't call them x and y anymore. We call them xi, which is this tornado-looking thing, and then eta, which is this fancy end right there. Okay. And so xi and eta, these are our parametric. We call these our parametric coordinates. Okay. And under these parametric coordinates, now that we have the shape function that looks like, or now that we have our element that looks like this, we can form our shape functions based on the form that we talked about for, 2D heat conduction, okay, with these specific coordinates. So under these specific coordinates, our shape functions have the following forms, right? And so N1 of eta and xi is going to be 1/4, 1 minus xi, 1 minus eta. And 2 of xi and eta will be 1/4, 1 plus xi, 1 minus eta, right? And 3 is a 1 plus xi, 1 plus eta. Okay. And finally, N4 is going to be 1/4, 1 minus xi, 1 plus eta. Okay. And just as an exercise, what you guys should try is that, given that the nodal coordinates for nodes 1, 2, 3, and 4 are given up above, try plugging these coordinates into these shape functions and see what you get. Okay? Because these shape functions are designed in such a way that, for N1, if you plug in the coordinates for node number 1, you should get a shape function value of 1. But if you plug in the coordinates of 1 to any of the other shape functions, you get 0. Okay? And so that's kind of the logic behind designing these shape functions the way that they are. Okay? So that, the corresponding, when you plug in the coordinates for the corresponding node into that shape function, you get 1, but for any other shape function, you get 0. Okay? Okay. And then once you have the shape functions established, what you can do is we can form functions for the mapping. Okay? And so this will be our mapping of physical coordinates, or I should say the mapping from the isoparametric coordinates into the physical space. Okay. And so I call these functions the mapping because, what these basically answer the question is that, because when we make this mapping, we're basically saying that every single point in this isoparametric square right here is going to be mapped into some location onto our, our base element, which is given by, this guy over here, right? And so what these mappings do is they answer the question and say, if we're on this location here in our isoparametric space, so that kind of X marks a spot right there, where would this be on our big element right here, or our physical space, okay? Because we basically need to make a one-to-one correlation. So you can almost think of it like a map. So you move kind of to one location in one space, that will put you into a certain location in the physical space, okay? And there's a one-to-one correlation, so that a location right here should correspond to a corresponding location in the physical space, right? And it follows kind of the similar rules, because all of these guys they look the same, even though they're different kinds of quadrilaterals. But if you're in the top right coordinate of the parametric space, say right here, that's going to put you somewhere in the top right coordinate of the physical space over here. Okay, but we need to make this mapping mathematical, and we need to make it explicit so that we can make use of it in our calculations later. And this mapping conveniently uses the shape functions which we have defined above. So we have x of xi and eta, okay? And so this is going to be x1, n1 plus x2, n2 plus x3, n3 plus x4, n4, right? And you have a similar expression for y as well, okay? And so basically what we can do is that, what we can do for this function, what this means is that we can take any coordinate, let's say xi naught and eta naught, right? And so let's say that xi naught and eta naught correspond to this location right here, okay? What we can do is we can take the xi naught and eta naught and plug this into our mapping function here, and this will give us the x coordinate of that, the physical x coordinate of this location, on our physical element, okay? And this is really important because, this mapping is we're going to use this for, whenever we evaluate any kind of integral expression, okay? And so this is just the x, and the y, looks exactly the same as this. It's just, you replace all the x's with y's. Okay? Let me turn on the lights real quick, and then I'll be back in a second. Okay, and so in addition to the mapping, what we can do is we can take the derivatives of the mapping with respect to the parametric coordinates, okay? Because you can see here from this mapping, this x of xi and eta, this is a function of xi and eta. So we can take derivatives of this, and get expressions for that. And luckily, conveniently, since the x1, x2, x3, x4, those are just constants, because those are just the coordinates for the physical space, element. When we take derivatives, all they do is they just land on the shape functions, okay? Right? And so we can have basically 4 derivatives here for our mapping. Right, so I'll write out one of them in full, but the rest are you can kind of extrapolate from there. And so if we take partial x, partial xi, then we get x1, partial n1, partial xi, right, plus x2, partial n2, partial xi, plus x3, partial n3, partial xi, plus n4, partial n4, partial xi, okay? So you can see here because the physical coordinates are constants, the derivatives only land on the shape function terms, okay? And so in addition to this, we have partial x, partial eta, we have partial y, partial xi, and we have partial y, partial eta, okay? And of course, what you can do from here is you can, in order to compute the shape function derivatives, you can basically just take the shape function which I have on this page and just take the derivatives corresponding to xi and eta, which isn't too hard just because these are just simply linear functions in those guys. Okay. And so the big important quantity that we need is that once we have all of these derivatives of the mapping, we can put these together into a single matrix called the Jacobian matrix. Okay, and so we call this matrix J, and so this matrix J is going to be equal to partial x, partial xi, partial y, partial xi, and then we have partial x, partial eta, and then partial y, partial eta. Okay. And so remember, this Jacobian is really important because taking the determinant of the Jacobian gives us our scaling factor in order to transform our integration bounds. Okay. Okay. And so, you know, what this means is that we can take, you know, this integral here, right? And so we just have an arbitrary integral of f dA, you know, where these integration bounds can be anything. And what we want to do is we want to transform these integration bounds to -1 to 1, because these are the integration bounds on our isoparametric element, okay? And then by performing that transformation, we turn our integration variables into d xi, d eta, okay? But, you know, because we're making this kind of fairly drastic change of the integration bounds, we can't just, you know, take one and induce the others. We have to have some kind of scaling factor in order to allow us to do this. And the scaling factor is given by the determinant of the Jacobian, okay? All right. Okay. And so, you know, before I kind of get further into further uses of the Jacobian, I want to take a little step because, you know, at this point, what we have is we have enough to basically perform, you know, Gauss quadrature, okay? Because once we have the integration bounds in this form right here, we can actually apply, you know, our Gauss quadrature to this in order to evaluate the integrals. Okay? So this is going to be similar to problem 3D on the homework. And so in 3D, you know, I've been kind of talking with a lot of you guys. I've been telling you to kind of follow the algorithm that we went over in class. But, you know, you don't have to perform every single step of that algorithm. So let me kind of walk through an example, you know, where we use kind of all the information up to this point to perform like an arbitrary integral in the, you know, with Gauss quadrature. Okay. And so this is totally off the cuff. So so I'll try to keep it simple, but you know, we'll see how far it goes. Okay. Okay. And so let's take just the simple integral, and we'll take the integral from let's do 4 to 10, and then integral from 2 to 6 of just the function x times y, and we'll say this is dy dx, okay? And we want to evaluate this with Gauss quadrature with a single point. Okay. And so the first thing that we need to do is, you know, since we're doing a 2D integral, we know that we're going to use a 2D form of Gauss quadrature. And so since we're doing a 1-point rule right here, the first thing that we need to establish is, you know, what are the Gauss, in this case, what is the Gauss point at which we're going to use to evaluate this? Okay? And so for a 1-point rule, you can kind of look back at the end of the lecture notes 11, which is going to be on 2D heat transfer. For a 1-point rule, we see that the Gauss points are going to be 0 and 0. So we do xi g is equal to 0 and a to g is equal to 0. And the Gauss weight is going to be 4. Okay. And so what we're going to do here is we're basically going to convert this integral, convert these integration bounds into the isoparametric bounds, and then use this Gauss quadrature in order to do that. Okay. Okay, and so let's basically follow all the steps that we need to do in the algorithm. Okay, so this algorithm starts on page 7 of the lecture notes 12 on isoparametric elements. Okay, and so let's start with step 1. And so step 1 is to establish the parametric coordinates, okay, for this Gauss point. Okay, and so we've already done that. And so we basically established that the Gauss coordinates are going to be xi g is equal to 0, and then a to g is equal to 0. Okay. Okay, and so step 2, what we want to do is we want to calculate the values of the shape functions at this point. And so what we're going to do is we're going to take our functions for the, our expressions for the shape functions, which we have on this page right here, okay? And then evaluate each of them at xi is equal to 0 and eta is equal to 0, okay? So we're going to have 4 functions, okay? Right? And so first we're going to have n1, and this is going to be a xi g, eta g, okay? And then we plug in for our expression for n1, so n1 is going to be 1/4, 1 minus xi g, 1 minus a to g, okay? And since we know that xi g is equal to 0 and a to g is equal to 0, we have 1/4 times 1 times 1, which is just equal to 1/4, okay? And so that's n1. And what you'll find similarly is that for all the other ones, so for n2 at xi g, a to g is equal to n3, xi g, a to g is equal to n4, xi g, a to g, okay? All these are going to be equal to just simply 1/4. So that's kind of the convenience of using a 1-point rule, because all these shape function values are going to have the same value, okay? Okay, and so now that we have that established, we can go ahead and move on to the next part, which is calculate the shape function derivatives at the Gauss points. Or in this case, at the Gauss point, because it's only one. Okay, and so at this step, we're going to have 8 different shape function derivatives to evaluate. So we have a partial n1 partial xi, partial n1 partial eta. Okay, and so the formulas for all these are given in the notes, and so I'm not going to repeat them all here because there's a lot. I have 8 of these to write down, but you can basically get these from the notes. So I'll write out this first one here. So partial n1 partial xi will be minus 1/4, 1 minus a to g, okay, which in this case a to g is equal to 0, and so partial n1 partial xi is going to be just minus 1/4. Okay, and then we're going to repeat this for all the other shape function derivatives here, okay. And in the end, we're going to have a matrix. So I'm going to put this into a 2x4 matrix. Okay, and I'm putting it in this matrix form just to kind of make it a little bit convenient later on, because we're going to be performing a lot of multiplications with this matrix. Okay, and so this is simply going to be, let's see here, minus 1/4, minus 1/4. Okay, and then we have 1/4 minus 1/4. So those are the N2s. And so the N3s are going to both be a positive 1/4. And then the N4 is going to be minus 1/4. And then 1/4. Okay. Right? And so there's our matrix of shape function derivatives. Okay. Okay. Step 4. And so step 4, I think, has been the part that is kind of confusing a lot of people on problem 3D, you know, given how this integral is, okay? And so step 4 basically is we want to compute the physical coordinates of this Gauss point. And so what we're going to do is we're going to use that mapping function that I talked about earlier and then evaluate it at the Gauss point, okay? Okay? And so basically what we're going to do is we're going to evaluate xg, okay, which is simply just going to be x, our mapping function, evaluate xi g and eta g, okay? And so remember, this is going to be x1 and 1, and this evaluate xi g and eta g, okay, plus x2 and 2, where n2 is again going to be evaluated xi g and eta g. Okay. And so all we got to do is just plug in, because we have all of these guys already, right? And so all the guys that are circled in green we computed in step 2, and so all those are just 1/4 actually. Okay, so fairly simple. And so the question now is, and I think this is probably one of the main questions that I got from the homework, is how do we compute this x1, x2, x3, x4 when all we have here are just integration bounds, right? And so how do we take these integration bounds and turn them into, you know, x1, x2, okay? And so to kind of help with this, let me draw the domain for this integral. Okay? And so our domain looks something like this. Right? And so we're just integrating over a square. And then the, let's see, so the x coordinate goes from 4 to 10, right? And so this is going to be x is equal to 4 on this side, and this will be x equal to 10, okay? And then our y coordinate goes from 2 to 6. Okay? And so down here is going to be y is equal to 2, and up here is going to be y is equal to 6, okay? And so if we do the same kind of numbering that we did before, we number the nodes just like that, we can write out the x and y coordinates for each of these nodes, okay? So node number 1 down here is going to be 4, 2. Node number 2 over here is going to be 10, 2. Node number 3 is going to be 10, 6. And then node number 4 is going to be, was it 4, 6. Okay. And so from this, we can write out the x and y coordinates for each of the nodes. Okay. Or we just did, but we can put it into this explicit variable form right here. Okay. And so from this, we see that x1 is equal to 4, and y1 is equal to 2. Okay. x2 is equal to 10, y2 is equal to 2, x3 is equal to 10, right? y3 is equal to 6, okay. x4 is equal to 4, and finally y4 is equal to 6. Okay. Okay. And so you can see some of these variables repeat because we're just basically integrating over a square. And so we can just kind of plug these guys in, you know, for that guy. Okay. And so if we do that, we can basically see, since everything here is just 1/4, you know, the x coordinate of the centerpiece, so basically the x-coordinate right here, which is just going to be the centroid of our square, is simply just going to be the average of all these x-coordinates. So we're going to do 4 plus 4 plus 10 plus 10, all divided by 4. Okay, and then what we get is 28 divided by 4. We get 7. Okay, and so this centroid right here has an x-coordinate of 7. And then the y-coordinate is just going to be the sum of all that. So we do 2 plus 2 plus 6 plus 6 divided by 4 is going to be 4. Okay? And so xg is equal to 7 and yg is equal to 4. Okay? And so that's basically the physical coordinates of our Gauss point. Okay? Because we know our Gauss point is going to be in the middle of this parametric square, right? Because that's what xi g and eta g is equal to 0, right? So this is 0, 0. And so if we take this point and then we map it into this domain up here that's defined by the integrals, what we get is a coordinate of 7, 4. Okay. And so that's the whole purpose of step number 3 right here. So, or step number 4, sorry. So step number 4 is we want to get the physical coordinates of that Gauss. Okay. Okay. And so that's step number 4. And so step number 5 is to compute the Jacobians. Okay. Okay. Right? And so the Jacobians can basically be computed as a product of two things that we've already basically established. Okay? Right? So the Jacobian is going to be equal to, first thing will be our shape function derivative matrix. Okay? Right? And so we computed this in step 3, right? Okay. And then to this, we're going to multiply this. We're going to multiply our physical nodal coordinate matrix. Okay. It's going to be x1, y1, x2, y2, x3, y3, x4, y4. Okay. And so this, we didn't explicitly do this in a step, but we saw these guys in step 4. Okay, so the previous one. And so by multiplying these, we get a 2 by 2 matrix. And so for this particular problem, I'm going to work it out. So we're going to have minus 1/4, minus 1/4. Right? That was the, yeah, oops. Wrong way. And then we have positive 1/4, minus 1/4. Okay. Positive 1/4, positive 1/4. Okay. And then minus 1/4, 1/4. Okay. Right. Yep. And then for our nodal coordinates, we're just going to plug in the ones that we got before. So x1 in this case is, what did we say? x1 is equal to 4. Right? We go 4, 10, 10, 4. 4, 10, 10, 4. Right? And this can be 2, 2, 6, 6. Double check. Yep. Okay. And so let me open up MATLAB really quick and perform this matrix multiplication. Okay. All right. So let's say call this n1, or n is equal to minus 1/4, 0.25, 0.25. We have minus 0.25. Okay. And then we have x is equal to 4, 2, 2, 6. Okay. So times x is 3002. Okay. So fairly simple. And then the one that we're really going to need here is the determinant. And so in this case, the determinant is pretty easy. So we're just going to take this multiplied by this. And so we get 6, right? And so our determinant of the Jacobian here is going to be 6. And so that's going to be our conversion factor, you know, as we perform our integrals, okay? Okay. And so that's step 5. So now that we have our conversion factor, next is going to be step 6. So we'll come back to step 6 in a minute. So step 6 is going to be, that's only relevant when you're computing basically element stiffness matrices. But in this case, you know, we're just doing a straight up integral. So we can skip step 6. Okay. And so step 7 in the step 7 in the notes basically says to calculate the value of the heat source or body force at the Gauss point. And basically, you know, the heat source and body force, you can kind of almost think of these as just simple integrands, okay? And so you can replace step 7 here, which is simply evaluate the integrand at the Gauss point. Okay, and so if you remember back from the start of our problem, our integrand here was just x times y, okay? And then our xg and yg was 7, 4, okay? So let's write that down. So integrand is just simply x comma y, and so this is from the problem. And so our Gauss point, so this is going to be xg, yg, okay? And so this is just going to be, in this case, 7, 4, okay? And so we plug these guys in, and we simply just get 7 times 4, which is 28. Okay. And so now that we evaluated the integrand, we're ready to transform the integral, okay? Okay. All right, so our original integral was integral from, this is 4 to 10, right? Yeah, integral from 4 to 10, and then 2 to 6 of xy dy dx, okay? Okay, and so this is going to be transformed into the integral from -1 to 1 of x of xi and eta times y of xi and eta, okay, times the determinant of our Jacobian times d xi d eta, okay? And then instead of evaluating this integral, we can basically use our Gauss quadrature. Okay. And so under Gauss quadrature, the evaluation for this is just going to be simply the sum from I is equal to 1 to the number of Gauss points times, let's see, xg, yg, okay, times the determinant of j times wg, okay? And so we have xg and yg, and we know that ng is just going to be 1 in this case. And so to evaluate this integral, all we have to do is take the product of xg and yg, which we have here in step 7, the determinant of Jacobian, which we have in step 5, which was just 5 in this case, or 6, sorry. And we have the weight. Remember, the weight for this one is going to be 4, okay? And so we pull this all together, and we get xg and yg, which is 7 times 4, times the determinant of Jacobian, which was 6, multiplied by our weight, which is 4, okay? So let me label all these guys. This is the determinant of Jacobian, and then this guy was the weight, okay? It's a Gauss weight, so not to be confused with weighting function. I know that they're almost the same, okay? And so we plug all these in, get 7 times 4 times 6 times 4, and what we get is 672, okay? And so that's basically how you would apply the algorithm, the isoparametric algorithm, to compute an arbitrary 2D integral, okay? And so you can basically use the same method for problem 3D in the homework. It's just that for problem 3D, you're going to do this with the 4-point rule. So you're going to repeat this 3 more times for the other Gauss points, and then you're going to sum up the results at the end. So remember, in this example, we just use the 1-point Gauss rule, which is at 0, 0, and then that's why we're able to kind of do this in one step. But the more Gauss points that you use, the more Gauss points you use, the more accurate it's going to be, but it's going to be more work. Okay? And so don't be afraid to use, your MATLAB code to help you, because it's a lot of tedious calculations. So if you can set this up in code, that's going to save you more work in the long run. Okay. And so before we kind of move on to strong and weak form, I do want to revisit step 6 in our algorithm. And so step 6, what this is this will allow us to compute the shape function's derivatives in the physical space. Okay? And so the key here is physical space, right? And so that means that we're going to, this will allow us to compute things like dn1 dx, okay? Because right now in the parametric space, we don't have this. Right? And so what we have instead are the shape function derivatives in the parametric space. So partial n1, partial xi, okay? And so, most of the times, we're fine with just using partial n1, partial xi, but for our element stiffness matrix, we actually need this first guy, okay? Okay? Because remember the form for our element stiffness matrix that we talked about at the beginning, okay? Okay. And so this gradient of W right here, what this is simply going to be, and so this gradient operator, this is taking derivatives in the physical space, okay? Okay? And so, transforming these derivative terms into the isoparametric space is a bit more complicated because they're not just, it's not just the function that we're changing, it's the derivatives that we're also changing, okay? And so, in order to basically deal with this, we need some help from a different function. Or I should say, I guess the term that we're using here is mapping, right? So mapping these is complicated. And so what we can do for the mapping is we can basically make use of the fact, you know, that we have our Jacobian, okay? Or we can make use of the chain rule, okay? Because what we can say is that even though we don't have partial n1 partial x, what we can do is we can write this in terms of the shape function derivatives that we do have, okay? And so we can say that partial n1 partial x can be partial n1 partial xi, which we have, right? Plus partial xi partial x, oh, sorry, multiplied by this. Okay. Plus partial n1 partial eta times partial eta partial x, okay? And so through this chain rule, you know, we can kind of cancel out these guys, even though it doesn't exactly work like that. But in order, basically, you know, we're able to get, you know, partial n1 partial x, okay? And so the nice thing about this form is that these ones we have in blue, so we have these already, right? And then these guys we can actually get. Okay? And the way that we obtain these is from the inverse of the Jacobian. Because remember, our Jacobian was filled with terms that look like this. We have partial n1 partial xi, or partial x partial xi, sorry. And we have partial y partial xi, partial x partial eta, partial y partial eta, okay? And so if we kind of turned our head upside down, you know, we can see that these guys look like what we need from here, okay? Except they're you know, flipped upside down, obviously. And so in order to kind of flip these, what we need to do is we need to take the inverse of our Jacobian, okay? And so that's where we get our j minus 1, okay? And so in order to get, in order to kind of compute the shape function derivatives as a group, what we can do is we can multiply our inverse Jacobian, which we can obtain easily, and we multiply that by our shape function derivatives in the parametric space, which I have in dark blue. And so remember, the symbol that we gave for that in those was B sub g, okay? And so this B sub g here is our shape function derivative matrix. In the physical coordinates. And what this is equal to is the Jacobian inverse, okay? Which you can compute from step 5. You just take the inverse of the Jacobian. And so, you know, most times you're going to let the computer handle this because it's, you know, computing inverse is kind of a pain. And then to this, you're going to multiply this by our shape function derivatives in the parametric space. And so remember, there's that 2x4 matrix that we had before for this. And so you can basically just multiply these guys together. And so that's why in step 3, you know, that's why I put those shape function derivatives in that matrix, because we use it in that form, you know, several times. Okay? Okay. And so that's what the Jacobian inverse is. So I want to make things pretty clear because I've gotten kind of several questions on this too. And so, you know, from that Jacobian matrix, we kind of use it for different purposes, but the purpose that we use it for depends on, you know, on what we're trying to solve. Okay. So let me kind of write it down here just to be clear. And so kind of the two main things that we get from the Jacobian. So we don't actually use the Jacobian by itself. So the Jacobian by itself is actually not that useful. Okay. But the first thing that we get from here is the determinant of the Jacobian, okay? And so the determinant of the Jacobian, this one is always, like basically always used, okay? And what it's used for is it's used for as a scaling factor in order for us to transform our integration bounds from the physical space to the parametric space. Okay. And so you're basically always going to use the determinant of Jacobian because you always need to transform the integration bounds, from whatever it was before into -1, 1. Okay. And so that's what the determinant is used for. So the determinant is a scaling factor which is used to transform the integration bounds. Okay. And so the other one that we use is Jacobian inverse, which you just saw. Okay. And so this is basically only used in the computation for element stiffness matrices. Okay. And so what they're used for is to transform the derivatives from the parametric space to the physical space. Okay. And this is something that we need for our element stiffness matrices, because that's the term that we're basically being asked to evaluate. Okay. And so remember, because transforming those derivatives is quite a bit more complicated. So that's why we need this kind of Jacobian inverse matrix in order to do that. Okay. All right. And so that's all the time I want to devote towards isoparametric elements. And so I want to make sure that I talk a little bit about strong and weak forms. But I don't have that much time. So I think what might be more useful is to go over one of the homework problems. Not that one. This one. Okay. And so let me do problem 3A from homework 3. Okay. So I actually saw this one kind of trip up a lot of people in the homework. Okay. And so problem 3A, what I want to do is repeat problem 2A, but I want you to assume that the solution is quadratic. Okay? So I like this one quite a lot because it kind of showcases kind of quite a few things and some wrinkles that we didn't have time to go over in the lecture. Okay, and so problem 2A, let's draw the geometry for it. Okay. And so in 2A we have the following. So 2A was a heat transfer problem. Right? And so we had a bar that looks like this. And so the length of the bar was L. The left side was a Dirichlet boundary conditions. We call that T0. And the right side was a Dirichlet boundary condition also, which we call that TL. Okay. We had no thermal generation. Okay. As we said that the length here is equal to 2.35 meters. Okay. The left temperature is equal to 10 degrees C. And the right and the T at L, this is equal to 65 degrees C. Right. And so the parameters here, the area was equal to 0.35 meters square. Okay. And the thermal conductivity was equal to 600 watts per meter K. All right. Okay. And so in 3A, what I said is I want you to assume that the solution is quadratic. And so what that means is that we're going to have 3 unknowns for both t of x and w of x. And so our t of x is equal to a0 plus a1x plus a2x squared, okay? And w of x, this is equal to b0 plus b1x plus b2x squared, okay? Okay, and so the first thing that we have to do for this, which I think most people got, was that we had to enforce our Dirichlet boundary conditions. Okay, and so this problem is unique compared to the ones that we did in class because this one has 2 Dirichlet boundary conditions. Okay? And so the first one is going to be the condition at 0, right? And so we say that t of 0 is equal to t naught, which is equal to 10 degrees C, okay? And so we plug in 0 into our t of x up here, and we simply just get a0, okay? And so a0 is going to be equal to 10, okay? And so on the flip side, for our weighting function, remember our weighting functions, what we require is that our weighting function disappear at our Dirichlet boundary conditions, okay? And so instead of, w of 0 is equal to t0, what we say is w of 0 is equal to 0. And so we plug in 0 up here, and what we simply get is that b0 is equal to 0. Okay. Okay. And so at this point, a lot of you guys, what you did was we just simply kind of plug these guys into our weak form. Okay. But we have to do actually one more step before we get there, which was we need to apply the other Dirichlet boundary condition. Okay? And so this one's a little bit unique because we had 2 Dirichlet boundary conditions. So when you have 2 Dirichlet boundary conditions like this, you have to apply both of them before you actually, turn it or submit it into, your weak form. Okay. And so let's go ahead and do that. Okay. And so our other boundary condition is going to be T at L, where L is equal to 2.35, and this is going to be 65 degrees C. Okay. And so we plug that in, we get A1 times 2.35. My stylus would stop being weird. Plus A2 times 2.35 squared, okay? And so what we get from this is basically 65 is equal to 2.35 A1 plus, was it 5.52 A2, okay? And so now we have another equation here, right? And so it'll be a little bit different than the first one because in the first one, we were able to solve for A0 directly. And so in this case, we're not going to be able to solve for either A1 or A2. Oh, sorry, there's going to be a plus 10 right here. Can't forget A0. But what we can do is we can eliminate one of these constants and solve that in terms of the other one. So then what we'll get in the end is just a solution with just one constant, okay? And so let's take this equation and let's solve it for A1, okay? Okay. And so we solve for this equation for A1, and so we subtract 10 from both sides. What we get is A1 is equal to 23.404 minus 2.35 A2, okay? And so again, we haven't eliminated, we haven't, solved for A1 outright because, we have A2 over here, but we can at least plug this back into our original T of X, okay? And so from this, we get T of X is equal to A0, which is going to be 10, plus A1, which is 23.404, minus 2.35 A2 times X plus A2x squared. Okay. And so this is the function that we're actually going to plug in into our weak form. Okay. All right. And similarly, we can do that W of L is equal to 0. Okay. And so this is going to be equal to 2.35 B1 plus 5.52 B2. Okay. So I just plugged in 2.35 in for L. And what we get from this is that B1 is equal to minus 2.35 B2. Okay. And then plug this back in. What we get is W of X is equal to minus 2.35 B2 X squared plus 2.35x plus B2 X squared. Okay. Right. And so you can see here, we haven't eliminated all the constant yet, so we need to use the weak form for that. But at the very least, we've eliminated one of them from the equation. Okay. Okay. And so in order to plug this in, now that we've applied both our Dirichlet boundary conditions, we're ready to plug this into our weak form. Okay. And so to plug into our weak form, what we need to do is we need to compute the derivatives. Okay. And so first we have dt dx. And so dt dx is 23.404 minus 2.35 a2 plus 2a2x. Okay. And then dw dx is just going to be minus 2.35 b2 plus 2b2x. Okay. Now we can plug this into our one-dimensional weak form. Okay. And so our weak form is just going to be simply dw dx times k times a times dt dx dx plus our source term is going to be 0, and this is going to be equal to, or sorry, this one's an equal sign, and this one's a plus. Okay. And over here, what we had is our Neumann boundary term, right? Which again is going to be equal to 0, just because we don't have any Neumann boundary condition. Okay. And so what we can do here is we can plug this in. Okay. Plug this guy in here. Plug this guy in here. Okay. Perform the foiling, and then we can get our last equation in order to solve for A2. Okay. All right. So let's go ahead and do that. And so right after plugging in, we first see that k times a is a constant, so they can just be pulled out of the integral. Okay. And we have an integral from 0 to L. Okay. We have 2.35 plus 2x, okay, as a times b2, okay. And then to this, we're going to multiply it by 23.404 minus 2.35 a2 plus 2a2x, okay, dx, and all this is equal to 0. Okay. All right. So the first thing I'm going to do is I'm going to cancel out all these constants, because we can, since we have a 0 on the other side, we can basically just divide by everything that's a constant. So the k times a is going to go away, and b2 is going to go away. Okay. Remember, we don't really care what w actually is. We're not actually going to solve for b1 and b2, but it's just, remember, it's just a tool to help us lower the order of the derivatives. Okay. Okay. And so now that we got that out of the way, we can basically perform this integral and solve for A2, okay, which is going to be here and here. Okay. And so after you perform the foiling, what you get is the following. Okay. So you get integral from 0 to L minus 55 plus 5.52 A2 minus 4.7 A2x plus 46.808 x minus 4.7 a2x plus 4a2x squared dx equal to 0. Okay. And now we can basically simplify and start integrating. Okay. And so after we simplify, we get interval from 0 to L of minus 55 plus 5.52 A2 minus 9.4 A2x plus 46.808 x plus 4a2 x squared dx, okay, is equal to 0, okay? And so if we perform this integration, and so we plug in for all that, and then what we get is minus 129.25 plus 12.972 A2 minus 25.96 A2 plus 129.7525, sorry, plus 5.777 A2 is equal to 0. Okay, we see that these two constant terms cancel out, right? And then all we're left with is just everything else has an A2 here, right? And so all these guys are going to basically combine into one term. And so the only way you can satisfy that equation is if A2 is equal to 0, okay? And so if we set A2 is equal to 0, then we finally get our final answer, which is T of x is equal to 23.404 x plus 10, okay? And you notice that this is the same answer as our analytical solution, which we got in problem 2a, okay? And so the reason we got the same answer here is because, you know, from our problem 2a, all we got was a simple linear equation, right? And so we just got, you know, this exact problem here. And so if you look at our approximate solution that we started with, you know, we had a linear term, right? So we had a0 plus a1x, right? And so it makes sense that the solution that we got kind of matches this guy exactly, okay? And so the reason we got a2 is equal to 0 is because, you know, there's no quadratic term in the exact solution. So if there's no quadratic term in the exact solution, there's no, it makes no sense for there to be a quadratic term in the, and the approximate solution as well, okay? All right, and so that's the review. So, you know, I know I spent most of the time on isoparametric elements, but that was kind of, you know, overwhelmingly the favorite topic for the review. So I wanted to make sure I covered that, you know, in detail, right? Okay, so, you know, if you have any more questions on this leading up to the midterm, you know, I'm always happy to answer this. I'm always happy to discuss. So you can, you know, email me, Discord me, you know, whatever's most convenient for you, right? And so best of luck studying for your exams. You know, hopefully this was helpful to you. And I'll see you another time.